Water. It is the lifeblood of our planet, sustaining all living things. From the smallest microorganisms to the largest mammals, water is essential for survival. Recognizing its paramount importance, the field of hydrology and water resources engineering emerged to study, manage, and protect this precious resource. This discipline explores the journey of water, from the atmosphere to the depths of the earth and back again. Water is a fundamental human right. It is also critical for agriculture, industry, and energy production. As our global population continues to grow, so too does our demand for this finite resource. This essay will delve into the evolution of our understanding of water. It will explore the challenges we face, and it will illuminate the innovative solutions shaping the future of water management. This journey through time will highlight the interconnectedness of our world. It will underscore the importance of global cooperation in ensuring a water-secure future for all. Join us as we explore the fascinating and ever-evolving world of hydrology and water resources engineering. At the dawn of the 21st century, our understanding of the natural water cycle formed the bedrock of water management strategies. We meticulously studied the continuous movement of water on, above, and below the Earth's surface. Evaporation, transpiration, condensation, precipitation, and runoff. These key processes became the pillars of our hydrological models. Traditional water infrastructure, such as dams, reservoirs, and canals, dominated the landscape. These engineering marvels aimed to regulate water flow, provide irrigation for agriculture, and generate hydroelectric power. We relied heavily on these structures to manage water resources and meet the needs of a growing population. However, as our understanding of the interconnectedness of natural systems deepened, we began to recognize the limitations of these approaches. We realized that solely focusing on engineered solutions could have unintended consequences for ecosystems and water quality. This realization marked a turning point in our approach to water management. It paved the way for more holistic and sustainable practices that considered the intricate balance of natural systems. As the 21st century progressed, the world faced unprecedented challenges related to water. A burgeoning global population, coupled with rapid urbanization and industrialization, placed immense pressure on our water resources. Climate change further exacerbated these stresses, leading to more frequent and severe droughts, floods, and unpredictable weather patterns. Traditional water infrastructure, once hailed as a symbol of human ingenuity, began to show signs of strain. Aging dams and inefficient irrigation systems resulted in significant water losses. Pollution from industrial discharges and untreated sewage further degraded water quality. Competition for water resources intensified, leading to conflicts among different user groups. The limitations of our existing water management practices became increasingly apparent. It was clear that a paradigm shift was needed to address these complex and interconnected challenges. We needed to move beyond traditional engineering solutions and embrace a more integrated and sustainable approach to water management. The 22nd century ushered in a new era of water management, powered by groundbreaking advancements in technology. Among these, quantum computing emerged as a game changer, revolutionizing the way we collect, analyze, and manage water data. With their unparalleled processing power, quantum computers could handle vast data sets with remarkable speed and accuracy. This newfound capability enabled the development of highly sophisticated hydrological models. These models could simulate complex water systems with unprecedented precision. They provided insights into future water availability, predicted droughts and floods with greater accuracy, and facilitated more informed decision-making for water allocation and infrastructure planning. The advent of quantum computing marked a turning point in our ability to address water challenges. It empowered us with the tools and insights needed to navigate the complexities of a changing climate and growing water demands. This technological leap paved the way for a more proactive and adaptive approach to water management, ensuring a more sustainable and water-secure future. Section 5. Nature as our guide, embracing sustainable solutions. Recognizing the limitations of solely relying on engineered solutions, the 22nd century witnessed a paradigm shift towards nature-based solutions in water management. Instead of viewing nature as a problem to be solved, we began to see it as a valuable ally. We learned to mimic and harness the natural processes that govern water cycles to enhance water security and ecosystem health. Green infrastructure such as rain gardens, bioswales, and constructed wetlands became integral components of urban landscapes. These nature-based systems mimicked natural hydrological processes. They helped to capture, filter, and infiltrate stormwater, reducing runoff and improving water quality. Restoring degraded wetlands, reconnecting rivers to their floodplains, and reforesting watersheds became key strategies for enhancing water storage, improving water quality, and mitigating the impacts of floods and droughts. By embracing nature-based solutions, we not only addressed water challenges, but also created more resilient and sustainable communities. Section 6. Harvesting from the skies. Tapping into atmospheric water resources. As water scarcity became increasingly pressing, innovative technologies emerged to tap into a previously underutilized source atmospheric water. Advances in material science led to the development of highly efficient atmospheric water generators, or AWGs. These devices, powered by renewable energy sources, could extract moisture from the air and condense it into clean, drinkable water. From small portable units designed for individual households to large-scale systems capable of supplying entire communities, AWGs provided a decentralized and sustainable solution for water-scarce regions. They proved particularly valuable in arid and semi-arid areas where access to traditional water sources was limited. The ability to harvest water from the atmosphere opened up new possibilities for water security. It reduced our dependence on groundwater and surface water sources, which were often overexploited and vulnerable to contamination. By tapping into this vast and constantly replenished resource, we could ensure a more reliable and sustainable water supply for future generations. Section 7. A global imperative: collaboration and data sharing for water security. Recognizing that water challenges transcend political boundaries, the 22nd century witnessed an unprecedented level of global collaboration in water management. International organizations, governments, researchers, and communities joined forces to address shared water challenges. Data sharing became paramount to this collaborative approach. Advanced monitoring networks, equipped with sophisticated sensors, collected real-time data on rainfall, river flows, groundwater levels, and water quality. This data, made accessible through global platforms, fostered transparency and facilitated informed decision-making for transboundary water management. The free exchange of knowledge, expertise, and technology enabled countries to learn from each other's successes and failures. It fostered a spirit of cooperation and solidarity in addressing one of humanity's most pressing challenges. Through global collaboration and data sharing, we could move towards a more water-secure future for all. Section 8. Education and advocacy: empowering future water stewards. Recognizing that sustainable water management requires a collective effort, education and public awareness campaigns took center stage in the 22nd century. From classrooms to community centers, the importance of water conservation, pollution prevention, and responsible water use was emphasized. Interactive museums and immersive exhibitions brought the wonders of the water cycle to life, captivating the imaginations of young and old alike. Citizen science initiatives empowered individuals to contribute to water monitoring and data collection efforts, fostering a sense of ownership and responsibility for local water resources. By educating and engaging the public, we nurtured a generation of informed and empowered citizens who understood the value of water and were committed to protecting it. This widespread awareness and active participation formed the bedrock of a sustainable water future. Section 9. A water-secure future. A vision of hope and resilience. As we look to the future of water management, we envision a world where every individual has access to safe and affordable water. A world where ecosystems thrive and water resources are managed sustainably for generations to come. This vision is within reach if we continue to innovate, collaborate, and prioritize water security. The journey through time has shown us that our relationship with water is constantly evolving. From our early understanding of the natural water cycle to the transformative technologies of the 22nd century, we have made significant strides in managing this precious resource. Yet, challenges remain. The future of water depends on our continued commitment to innovation, collaboration, and education. By embracing a holistic and adaptive approach to water management, we can create a more sustainable and equitable water future for all. Let us continue to work together to ensure that water, the essence of life, continues to nourish and sustain our planet for generations to come.